With that, I'd like to introduce our first speaker. So Dr. Aaron Gallant. Aaron is an assistant professor of geotechnical engineering in the Civil and Environmental Engineering Department here at the University of Maine. He received his BS in civil engineering from Tufts University in 2009, master's PhD degrees civil engineering from Northwestern University in 2011-2014. Prior to joining UMaine in fall 2016, Aaron provides instruction in the area of geotechnical engineering and performs research on a broad range of topics, including foundation engineering, ground improvement, and natural hazards. He is also the TIDC Thrust Area 3 lead. He has received recognition for mentoring graduate students in research, including UMaine's Faculty Mentor Impact Award, the ASCC Directors Award for Outstanding Faculty Member, and the Young Professor Paper Competition Special Recognition Award from the Deep Foundations Institute. Well done. Aaron.
Thanks, Aaron. A lot of Aarons going around here. So I'm going to kick it off today a little bit from the academic perspective, talk about a project that we've been working on here with my colleague, Warda Ashraf, and then the graduate students, Bilal Hossein, who's really led a lot of this work. And I also want to mention here another graduate student, Danilo Botera Lopez, who's really provided a lot of muscle and helped get some of these experiments off the ground that I'm going to show you today. So what I'm going to talk about today is really the scaling of an innovative or new subgrade stabilization method in the lab, and start thinking about what's next, and kind of sticking to this, research and development process of ideation, advancement and development, and technology transfer. So we've heard some of the DOT folks talking about the challenges in New England, freeze-thaw cycles, the fact that these things are increasing, okay, and our pavements and roadways are going to be subjected to more cycles of this type of distress. Mentioning here real quickly here, one of the big goals of the University Transportation Center program in general is really, if you look at it, is advancement and development of emerging technologies. They really want to see us pushing that forward, and then also enabling technology transfer and deployment, to achieve some of these desired societal outcomes here. So these are some of the big strategic goals of the UTC program, and we're operating in here thinking about that. Just quickly here, before we get started, I just want to say that the subgrade quality has a substantial impact on the design and cost of pavement structures. And for those of you that aren't familiar here, looking up in the top left corner, usually you have this asphalt or rigid pavement system followed by a base. You may have a sub base, but then the subgrade down here as well. And if we think about the surface loading, really you're going to get this stress decay interacting. Big piece that I want to show here, if you look at this blue curve, we're going to look at things in terms of CBR, the California bearing ratio. It's a really common parameter or measurement used as an indicator of the subgrade quality. It's really a normalized stiffness, if you will. And so when you start thinking about here about the required base thickness, which is certainly going to go into some of the cost, you see that this really starts to decrease as your subgrade quality increases, is really what's being indicated down here on the bottom. If you want to start thinking about this in terms of cost, here I'm showing on the horizontal axis here, basically the equivalent single axial loads, that might be exposed to a pavement, and the cost of different materials. The red line here is the asphalt, but just thinking about the base in general, this comes from the FHWA. We can see that as we go down here, the subgrade CBR, or subgrade quality, as that increases, this cost drops substantially. I mean, so the subgrade material does play a big role in our pavement structure and the cost that goes into it. Here, there are approaches to engineer poor subgrade soils. I'm showing some pictures here. These aren't paved roads, but I really want to illustrate what's going on beneath the pavement. When we think about the freeze-thaw cycles and we get to the spring, things are wet, really that material becomes very weak, okay, very weak. And this is what's going on. We don't get potholes quite this extreme once we have pavement in a proper pavement structure. But this is what's going on, especially in New England and other areas subjected to this type of thing. So you can generally think about stabilizing or improving the subgrade with excavation and replacement. Geosynthetic stabilization, probably to some mixed degree, maybe some problems with strain compatibility here, but then also chemical stabilization. And this is really the mixing of cement, lime, or some chemical additive that will react and create a binder in the soil. And so what I'm going to focus on here is this. All right. So we're talking about that. What I'm going to talk about today and the method that we're thinking about is accelerated carbonation, really using accelerated carbonation as approach. And so what we would be thinking about is mixing hydrated lime, water in the soil, same as you would now for conventional lime stabilization, and then injecting CO2, okay, or basically carbon dioxide would be consumed during the reaction. So the CO2 would come here through the soil, it would dissolve in the available pore water formed by carbonate, and then calcium carbonate, which is going to be our binder, would precipitate out, okay? It would also produce some water here and heat. So I'm going to show you some lab experiments here going forward. We're talking about lowering the carbon footprint, getting greener. If we think about the cycle of where hydrated lime comes from, well, it really starts out as calcium carbonate, really what's going to ultimately be our end product. So when you get limestone here, you got calcium carbonate, it's typically burned. We have this calcination process. We're going to heat it up, and there's going to be process related CO2. In other words, when you heat up the calcium carbonate, you're going to emit CO2 in the air. And then we also have combustion related CO2 as well. So we have both of those going into it. But when we come all the way back around, really 2/3 of that CO2 emission is process related, and we're ultimately going to consume that back. So we can think about dropping the CO2 emissions by 67% relative to, say, conventional lime stabilization. And so that's another benefit there when we're thinking about green. So in our testing that I'm about to show, we went ahead and used a soil that has a very high, okay, frost susceptibility or susceptibility to frost action. All right, in this case, basically a non-plastic silt with low permeability, but low plasticity, low thermal properties, basically considered very high as you can get here, as you can see from this FHWA frost susceptibility criteria. So we went extreme. What we're attempting to simulate here, and I'm trying to draw, maybe not so well, an embankment here. We're going to have some lime mixed soil that you could think. This is where we would be performing subgrade stabilization. And what we're trying to simulate here is basically create some symmetry in the lab and carbonate basically a portion of that embankment, all right, to try and simulate some of these processes. And if we go ahead and take a look at that, where we would be injecting CO2 is perhaps at the center line of this highway embankment. So we're using symmetry here, as you'll see in the next slide, and that's where we would inject CO2. And it would ultimately be able to migrate laterally. If this was a full embankment, it would also go the other way as well. So give you an idea of what this looks like. This is basically a half lane width. So looking at this is kind of this picture has been compressed a little bit here, so it's a little distorted. But we got an embankment down here on the side. We have put holes in the side of this box, okay, so to allow gas to pass through as well. And we've created basically an equivalent porosity, if you will, through that wall by drilling holes and then filling it up with soil. But we needed some confinement to build the box as well. So just to kind of talk about here, we had thermocouples. It was heavily instrumented, but I just want to give you a couple indicators here. This red line, which is associated with the amount of CO2 gas that we're putting in. So as we're injecting CO2, we see the heat at different depths, which is black line would be shallower, blue lines would be deeper. We see those temperatures rising, which indicates that yes, our reaction is occurring. We go to the end, we did go ahead and evaluate and measure what the binder content was in the soil. Okay, and if you come up here to the top, basically 150 millimeters, okay, 6 inches, you see that basically we achieve full carbonation. Number one, here's our binder content, what we theoretically predict based on the amount of initial lime that we consumed, and there was no lime left in the soil over this depth interval. We did mix lime in with a second layer here. What we look at here is our second 6-inch lift. though we had very minimal carbonation, except right at the very top. So this did not penetrate deeper. Typical or conventional chemical stabilization, you're usually trying to achieve anywhere or cement anywhere from 6 to 12 inches. So we did achieve that lower limit. We're still looking into the physics of gas flow a little bit here to understand how we could penetrate deeper in the soil. But one of the key things to keep in mind is that you will need a continuous air phase to achieve this efficiently. It is worth noting here, another thing we did was we took shear wave velocities, a measure of shear stiffness in the soil as well. If we look here within that carbonated zone, we see that we have a dramatic increase in the shear wave velocity here. And we start seeing these things happen over 6 to 10 hours, really is where things start to pick up. And so this process is very rapid, and that is an advantage for using carbonation over some of these other chemical stabilization methods. If you need to deploy something rapidly, or you want to verify how well you're doing rapidly in the field. How stiff was it? What are we achieving here? Well, these shear wave velocities are equivalent now to very dense soil and soft rock, okay? So this is becoming highly cemented. If you're on the tour today, we can even walk out behind the center. The box is still there, or it was still there the other day, and you can even go ahead and we can feel this later on. And then I mentioned that we performed the CBR. So here we use the field CBR as a way to do this. You see our load frame. And so really we're going to go in and measure the stiffness of this material as well, using something that can be conveyed to DOTs and practitioners readily. So what I'm starting off here is I'm going to demonstrate here that carbonation did substantially increase the CBR value. If we're looking here, this is what we had before. I'm showing here criteria at the bottom. Basically, what would be considered a good, very good, or excellent sub base, and then for a subgrade, very good, fair, poor, or very poor is what you're looking at over here. So we compacted this relative compaction of 80%. And so we're up around basically a fair to good to very good sub base initially. All right. And that's a good starting point. You can see that we did increase the CBR significantly, especially up at the top where there was a lot of carbonation. And so we can see how that varies with depth. And so now we're getting in not only to having a very good subgrade, but moving into something that would be considered a very good sub base. All right. So a dramatic improvement there. A couple of things to keep in mind here, and this is what I'm going to point out as we move forward, is this is not a soaked soil, all right? It's that soaking condition. It has a very large influence on the California bearing ratio, or CBR, all right? And so that's in a good condition, right? And any bad soil, any camp road, if you've driven on that here, is stable in the summer, right? It's dry. It hasn't been exposed to a lot of moisture or just been through those freeze-thaw cycles. So what we did after this was we went into the lab and we went into an environmental chamber. We have a pretty intense setup here, but what we were trying to do is simulate that vertical freezing front, okay, that the subgrade is exposed to. So a vertical, basically top-down freezing front. We would then heat the environmental chamber up, create a thaw cycle, and we repeated that twice, okay, to go ahead and assess the durability here of this carbonated soil. So first thing starting off here, as I mentioned, we soaked, all right, we wanted to make sure our soil was saturated before we performed these freeze-thaw cycles. We wanted to have plenty of water in there. That is going to immediately drop, okay, this is before any freeze-thaw cycles, the CBR, but this is associated only with soaking. So really our new reference point here is we want to see how things change from this point right here. How is it going to hold up as we start imposing those freeze-thaw cycles? As we went through this, I'm not going to spend a lot of time here, but I'm going to focus up here at the top of the soil column, where we started with basically shear wave velocities of, over 600 meters per second, ended down here at 450. So we're still sitting in this range where we're considered a very dense soil and soft rock. And this is after multiple freeze-thaw cycles. Below that, untreated soil, we started around 250 meters per second, and that shear wave velocity is decreasing to about 150. So we're down here in what would be considered a soft soil profile now. And when we continue on, we'll see how those CBR values change. So as I mentioned, we're looking at this value right here. This is our reference point before any freeze-thaw cycles were performed. This red diamond that you're seeing, we soaked. So we went from this initial condition, all right, we increased the water content, and we got this drop in CBR that I mentioned before. After multiple freeze-thaw cycles, we see that this holds up. All right, it was very durable, the carbonated soil to these freeze-thaw cycles that were imposed. If we go to this untreated or uncarbonated soil, we see that when we looked at the frost susceptibility criteria, okay, this would be considered very high, all right, based on the post-freeze-thaw cycle CBR values that were measured. This corresponds to, that table that I presented earlier. That's what's anticipated. And so in this case, this method worked reasonably well, okay? So a couple of things sticking along this idea of basically crossing this gap, this innovation gap that Aaron mentioned before. A lot of times just generally we're thinking about, can we come up with some good ideas? We have some good ideas, and these selection, may or should be driven by cost and value engineering, immediacy of impact, potential long-term benefits. Is it feasible? Can we do it? That's part of what we were trying to achieve here with these larger bench scale experiments. Durability and resilience, right? The name of the center. Decision and potential adopters. Finding early adopters who will support this is also going to be very key to crossing that innovation gap. So folks that are interested and see a potential ability, and then demonstrating the ability to investigate. And so that's kind of where we are now. And as we grind through this processing and we start off with our initial testing, we need to figure out what went well, what did we learn? Are there things that we could refine? And sometimes a subset of these good ideas still won't work. And sometimes we can grind through this and we achieve some successes here through, bench scale modeling, developing an engineering approach that we can describe how it works and when and why it works well. That's very important. And then also, publications for help for acceptance. And so when we think about soil carbonation in general, what I would highlight is that, it provided comparable or even better strength and stiffness to conventional lime stabilization, which, by the way, would have really limited effect in a non-plastic soil with a high frost susceptibility that we saw today, right? It's better for clays or things with high plasticity. The binder was relatively durable, okay, in the soil. We had rapid cementation. I consider that advantage because, number one, you can verify it quickly and you can figure out how to deploy it quickly in the field. And it substantially reduces the carbon footprint associated with the material production. Okay, so we are consuming a lot of CO2 in that process. I will note, though, it does require an added step compared with conventional lime stabilization, where we're mixing and basically leaving the site. We're going to have to mix and then ultimately add CO2. But it doesn't take a long time. We've demonstrated that can happen quickly. So what's next is we really need some industry and DOT partners that would be interested in exploring this further and see a potential benefit. One of the things is thinking about the incentive processes. What could potentially make this more interesting to people? What's the incentive to consider carbon in construction processes at this point? What incentive or monetary incentive do contractors, DOTs, and consultants really have to apply something that would reduce the carbon footprint? One policy change could make a big difference in what's considered. As academics and everything else, we're being told this is a big problem. We need to help contribute to this issue, but there needs to be incentives in place for us to ultimately start moving the needle here. When we think about technology transfer, this is really moving inventions, concepts, or designs to creators or public or private users. And so while we need our business partners, we need to also kind of understand here the relationship with creators, businesses, and DOTs. And some of the folks following me are really going to be able to kind of highlight their experience there. But these creators and businesses need to implement it commercially, find early adopters within the DOT, and need to get something contracted. And this can be the really hard part. And I've talked about with my colleagues over here to the left here, this, there are non-competitive options, where we can specify new concepts and inventions as a demonstration project. Really, this is an experimental process, and probably this is where I see us being able to try or use some of these contractual mechanisms to try some of these things out in the field. So I want to thank everyone, thank the TIDC, and I think I'll welcome Gary up next.